Hello, everybody. It's not too early to start thinking about your test number one. Some folks will call it exam number one, that'll be held in your thermodynamics class soon. So let's get started with some ideas on how can you prepare to perform well on test one. So here we go. Are you allowed to use a formula sheet? Are you going to be creating your own formula sheet, or will you be provided a formula sheet by your instructor? Want to have a couple of remarks about formula sheets. I have never been a fan of formula sheets for thermodynamics class. When I was a student, when I was you, we did not have formula sheets in thermodynamics. We were allowed formula sheets in kinematics classes, in some mechanical design classes where there were applied formulas that applied to specific situations. Not so in thermodynamics. So this is what my formula sheet looked like when I was a student. But I do want to make the point that this is your best formula sheet. So I want to encourage you to think about what are the fundamentals that are most important in thermo, and commit those things to memory. And some of the other things that you might put on a formula sheet that might be specialty equations, recognize that you can derive those quickly in a test situation. So I'm going to review with you things we all know about thermodynamics. And this little presentation is dedicated to one of the most inspiring individuals that I ever knew, probably the person who had the most influence on my professional life beyond my parents, and that's Dr. J.B. Jones, who was department head when I was a student, and he also was a thermodynamics professor. He was an inspiring educator and engineer, and he gave most all of us students the confidence for us to try achieving things that we never thought we could achieve. So the next discussion is dedicated to the memory of Dr. Jones. Oh, and he was able to do this. He could stand in front of us as we were preparing for a test, and he could capture these fundamentals on a chalkboard, writing with chalk on the chalkboard in a matter of a few minutes. And we would feverishly write down what Dr. Jones was writing on the board. And then we would go back and study that material, try to get it in our heads so that we could perform well on his thermodynamics tests. So this section is things we all know about thermodynamics up to test one. So this is comprehensive only up to test one. And what I'm trying to do is anticipate where you might be in your class. So recognize that there may be some slides here that it's material that you have not covered. And so, of course, you want to be asking your instructor about test coverage in your specific class. So this is where we know stuff up in our heads. Also, this is where we plan our work as we're performing on a test. We got pencil and paper. We're going to be writing things down. So this is where we plan our work. The first thing we do, we read a problem. You decide, is this problem an open system or is it a closed system? My suggestion is you write that down after drawing a sketch or a PV diagram or a TV diagram on your solution. Write down one or the other of those. The next slide is definitions, and Dr. Jones would capture these a lot like I've tried to do in PowerPoint. And he reminded us all of that is up in here. It's not going to be on a formula sheet. Remember absolute temperature. If you're in degree C, you want to add 273 to get to degrees K. Or in English, you have degrees F, you add 460 to get to degrees R. Pressure, it's an intensive property. You have a pretty good working knowledge of what's a gauge pressure, what's an absolute pressure, and you're simply adding the pressure of the surroundings, usually 1 atmosphere, to get to absolute pressure. Volume, capital V, that's an extensive property. And then you know the intensive property is little v, which is V over M. Know that in your head. Density, it's the reciprocal of specific volume, intensive property. Internal energy, capital U. Remember, little u is the intensive version of internal energy. It's capital U over the mass of a closed system. So you've learned enthalpy. Enthalpy, it is also a property and is defined as U plus PV. That's all you, at this point, that's all you really need to know about the property enthalpy. It's just U plus PV. So, and then you also know that a set of properties, a combination of properties, is what defines the state of a substance, whether it's an ideal gas or a phase change substance. You know the definition of work and power. So the fundamental definition of work is moving a force through a distance, integrating F as a function of X, F dx. W out, W greater than 0 means work is done by a system. That's our convention in this class. W dot is the rate of doing work. We put a little dot over top of W to designate the rate of doing work in watts or joule per second, or Newton meters per second, or horsepower, or BTUs per hour. Heat transfer. What's the difference between heat transfer and work? The difference is that heat transfer, both heat and work are boundary phenomena, but heat, you can identify heat transfer due to it flowing from a high temperature to a low temperature. Heat flows from high to low temperature on its own. Now, jargon that I hope you have in your head, man, you might be given a test problem that says adiabatic process, and that's all. That immediately tells you adiabatic process. That's an example where the system is fully insulated. There's no heat transfer, no heat flow. Q equals 0 for an adiabatic process. You've gotten good at interpolation. Okay. You don't need to, you should be able to figure out the formula by writing down a little table on your own to interpolate for Y when you have X. You should know the definition, the fundamental definition of specific heat. C sub P and C sub V are partial derivatives. We really, in this course, we don't do anything numerically with these partial derivatives. What we pray for is an ideal gas where properties of an ideal gas depend on temperature only. That's what enables us to transform those partial derivatives into ordinary derivatives. And then we have a pretty good idea of when do I use CV? That's when I need to, when I'm looking for delta U. When do I use CP? That's when I'm looking for delta H. Okay. CV, you can use it for any process. It doesn't have to just be a constant volume process. You use C sub P anytime for an ideal gas when you're looking for delta H. Do you ever find heat flow at the system boundary? And so some statements about it, if you can identify heat flow for a closed system, Qn is greater than 0, that means heat flows into the system. Now, for an open system, you're probably just getting started with open systems, and your textbook is famous for using little Qn. That'll have units of kilojoules per kilogram, and it's defined as Q dot, the rate of heat flow, divided by M dot, what's flowing into and out of a steady state control volume. Little Qn for an open system is Q dot over M dot. Work for a closed system, W out at greater than 0 for a closed system. And remember, for quasi-equilibrium processes where we have the path, you calculate the work out by the integral of PdV. Very important equation that you should have in your head. it's not going to, simply blindly writing this on an equation sheet's not going to do you a bit of good. Okay. On the open systems where things are flowing in and flowing out, recognize that the textbook uses little w, kilojoules per kilogram, to represent W dot, the output power, divided by M dot, the steady state mass inflow and outflow of an open system. Continuity equation, also known conservation of mass, applies for a system and a control volume. So don't you think that most of your work for test 1 is going to be probably closed system problems? Probably. That's my expectation for test 1. Okay. I've drawn a piston and cylinder as a good example of a generic closed system going from state 1 to state 2. So what's a statement of continuity? Well, continuity says the mass at 1 equals the mass at 2. There's no mass inflow or outflow, so we just call that M. For a control volume, a little more complex. By far and away, most of your problems in thermodynamics class are going to be steady state, steady flow. So I've shown sort of a generic control volume. This is a schematic of a turbine process. I've shown, but for steady state, steady flow, the mass inflow exactly equals the mass outflow for steady state, steady flow. Okay. For multiple inlets and multiple outlets, the sum of the mass flows in equals the sum of the mass flows out. And then I put this later near the bottom of the slide because it's going to be very much unexpected on test 1 that you would have a problem that involves a transient mass flow system. But there it is. Okay. And down at the bottom of the slide, M dot equals rho AV. Commit to memory. Of course, if you're allowed a formula sheet, of course, put this on your formula sheet if you can't remember it. For steady flow, uniform flow across the flow area, M dot equals rho AV. Very important. M dot is rho AV. Many students gloss over that, and in test situations, if you have an open system or control volume, same words, you're going to be using M dot equals rho AV. That's almost like a starting point for these type of problems. Also, in many homework problems, the volumetric flow rate, A times V, is given. It's another important thing to remember in your head. Volumetric flow rate, A times V, area times velocity. Okay. The first law of thermodynamics, conservation of energy for a closed system. Of course, you would put this on a formula sheet for panic situations. In case you panic, you have that written down. However, my expectation is that you have it in your head. You should be able to write this down from what you have in your head for a closed system. Q in minus W out is equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy plus the change in any other energies that are given in the problem statement. Now, some of you may or may not have covered systems operating in a cycle. It's systems operating in a cycle. And so if you have, I would chase you to my video where I went through a detailed example problem for one of Dr. Barbish's problems for a system operating in a cycle. And you could pick up on that. That I don't know if your specific class has covered systems operating in a cycle or not. Okay, so that's first law for a closed system. Now let's look at a first law for a control volume or open system. So here we go. The most general application, and I don't expect that you're going to be introduced to this general statement of the first law of thermo until a day or two before your test. Maybe not. But here is a generic sketch of a control volume, open system, one inlet, one outlet. Okay. And so the general statement of the first law says Q dot in minus W dot out rates equals the rate at which the control volume changes its contained energy, that's transient, plus the sum of the M dots leaving, H leaving, plus kinetic energy leaving, plus potential energy leaving, minus the sum of the M dot ins times enthalpy in, kinetic energy in, potential energy in. So very complex. Would be totally shocked if you had to use something like this in a test situation. You might have something steady state, steady flow open system where it with one inlet and one outlet, the two mass flows must equal. That's the continuity equation. And then the statement of the first law of thermodynamics for an open system, two ways to write it. Q dot in minus W dot out is equal to M dot, the inlet and outlet are the same, times change in enthalpy, HE minus HI, plus change in kinetic energy, VE squared minus VI squared over 2, plus change in potential energy, Z height times G. And then if you divide all of this by the mass flow rate, M dot, you get the textbook statement, little q in, kilojoules per kilogram, minus W out, kilojoules per kilogram, equals delta little h plus delta little ke plus delta little pe. If your class has covered cycles, and there's a good reason for that, we're going to be in nearly the rest of this class, we're going to be talking an awful lot about systems operating in a cycle, power plants, refrigerators, various heat pumps, things like that. And so if you have covered this in your class, I'll leave it this for you to go back and look at the static slide for this. But this could, even a sketch like this, if you've covered systems operating in a cycle, very powerful thing to put on your formula sheet. This is a statement of the first law for a system operating continuously in a cycle. Q dot H minus Q dot L equals W dot net. Only applies to cycles. Thermal efficiency, same remark here. I'm going to gloss over this slide because some of you, the classes, may or may not have covered thermal efficiency or coefficient of performance for cycles so far or not. Now let's look at some material that you definitely have got to have in your head. Got to have this in your head. Types of problems that are ideal gases. Okay. If it's an ideal gas, use the ideal gas equation of state. Okay. So for a closed system, there's 3 statements of the ideal gas equation of state. They are all identical. Understand why they're identical. PV equals MRT. P times little v is equal to RT. P equals rho RT. Okay. You should know how to use those. We've had a good number of homework problems where this is used. Remember, what's R? The gas constant. It's R bar over the molecular weight. I hope you have R bar committed to memory, both the numerical value and the units of R bar. Okay. So the jingle for closed systems, here, the left-hand part of the screen, for closed systems, since the mass is constant, the jingle, P1 V1 over T1 equals P2 V2 over T2. Very powerful, but only for closed systems that are dealing with ideal gases. Open systems where you have things flowing in and flowing out. Notice here, there's no M. We don't deal with masses, we deal with M dot. And so the state ideal gas equation of state at any state is P times little v is RT, or identically, P is equal to rho RT. You've got those things in your head, I hope. We're talking about ideal gases. So for any ideal gas, the change in internal energy is the integral of CV dt. For any ideal gas, the change in enthalpy is the integral of Cp dt. If you're told, I want you to use variable specific heat, that's your signal to go look up these properties in tables, like an air table or an ideal gas table in the back of your book. Under all situations, this is an identity true for all ideal gases, Cp minus Cv is equal to R. Cp minus Cv is equal to R. Remember, K is the ratio of specific heats is defined as Cp over Cv. I remember a couple of homework problems where you were given K and not given Cp or Cv, and you had to figure out what is the value for Cv or Cp when K is given. And you got to remember that this identity is what saved the day. Cp minus Cv is R. That enables you to get to one equation, and one unknown for K equals 1.35 or 1.4. Okay, that could show up on a test. Now, what you're praying for on a test is an ideal gas, and the instructor says, consider the ideal gas to have a constant specific heat. So in that case, the integrals become easy for ideal gases with constant specific heat. Delta U is simply Cv times delta T, and delta H is Cp times delta T. Very powerful. So you're praying for your instructor on the test to say, consider air to be an ideal gas with constant specific heat. That's what you want. That's what you want to read. We had a number of problems using the compressibility factor. Okay. Notice how similar the ideal gas equation of state is compared to the when you have gases that don't behave exactly like ideal gases. Ideal gas equation of state, PV equals RT. For gases that are not exactly like an ideal gas, PV equals ZRT. Use your eyes to see how similar. You see over here, for an ideal gas, it's like Z equals 1. Okay, so Z equals 1 would be ideal gas behavior, wouldn't it? Okay, that's what this is all about. And so when you're asked to, when you're given a gas and then you're instructed to say, determine Z, remember that you have to go to a graph. You have to go a graph in the back of the book. And so now is when you strategize. We're preparing for a test. Do I think my instructor is going to hand out paper copies of this chart that you're looking at, this graph, or is my instructor not going to do that? There's nothing wrong with you asking. There's nothing wrong with you asking, will we be working with Z on the test? You might get a straight up answer, yes or no. If the answer is maybe, then you want to ask, well, then how will we get to the Z chart? And that can help you decipher. That can help you decide how much work, how much time am I going to invest on studying on this or not studying on this. So this is where your relationship with your instructor is going to come in handy with your time planning as you prepare. Wow. So many of our homework problems and so much of your work time has been spent evaluating properties for substances that can change phases. You must have in your mind a picture in your mind of this pressure volume diagram with the vapor dome, and you must have in your mind what these phases of substances are and how they relate to the dome. Another thing you must have in your mind is remember X. Remember the definition of X is quality. X is quality. It's defined only under the dome where you have a saturated two-phase mixture. You have a mixture of saturated vapor and saturated liquid, and X is the ratio of saturated vapor divided by the total mass, the liquid plus the vapor masses. And so that's what enables you to, in your mind, to write down this relationship. X is equal to V minus VF divided by VG minus VF. It's a ratio, okay? Or yeah, it's a proportion. So I hope you have this in your mind. And also remember, as we work through homework problems, this is the way you would determine, say, little u or little h underneath the dome. You would use the definition of quality to do that as well. Certainly would be valuable to put this kind of information on your formula sheet if you're creating it on your own. Oh, there was this box down at the bottom of the slide. When you have a compressed liquid, we've got a really neat engineering practice is when our phase is in the compressed liquid region, we look up V, U, and H in the temperature tables as saturated liquid. So V becomes V sub F at the temperature of the liquid. U becomes U sub F at the temperature of the liquid. And so that's a very good engineering tool when our phase is in the compressed liquid. There are chances you're going to be faced with that in your test situation. Yes. Okay. That completes things we all know about thermodynamics. Dr. Jones's expectation of us as students was that we had that in our heads. Okay. And his tests were very fair. There weren't tricky problems. They were right down the middle of the fairway. And we sank or swim based on our understanding of those fundamentals that we had in our heads and our ability to apply them in a stressful, time-limited situation. Reminders for good performance on your test. Start with a sketch. Draw something down for each problem. Okay. Show and explain your work. Don't just write down formulas and calculator work. You got to explain your work. It doesn't have to be beautiful sentences, just some phrases, things like that. Work down the page. Don't make it this gunshot look. Somebody's looking at your work and trying to give you partial credit where you got off track. I need to give this person as much partial credit as I can. Do yourself a favor. Work down the page. Start each problem on a new page. Okay. You probably figure I've graded lots of thermo tests. These things help me help the students who need partial credit because they got off track somewhere a little bit. Okay. In yellow, when you're stuck, you will probably it's inevitable. You will get stuck on a problem. And it's time limited. What do you do? When you're stuck on a problem and you just don't know what to do, write down the first law of thermodynamics that applies to your problem. If it is a closed system, write down the first law for a closed system. Study it. Take a little time to study it. Oh, is there something I could get here? Can I get something, some term? And this may help you very quickly. The light bulb go on for you, and then you see how to solve the problem. So this is something that Dr. Jones always encouraged us to do. When you're stuck and you just don't know what to do, write down the first law. It can really, really help you. Okay, another reminder. This is so Seneca was a well-known Greek philosopher way back when. And he says, luck is a matter of preparation meeting opportunity. So that's a well-known phrase. And so how does this apply to you all? My thought is, and as you get ready for test one, knowledge, your knowledge plus your ability to perform, to apply that knowledge, to perform on a test, the sum of those things is what's going to get you a good grade. Knowledge plus performance. So look, this is my my parting shot for you. Take some time to prepare. I wish you all the best for good performance on your test, and let me know what I can do to help. Don't hesitate to email. Don't hesitate to get on the online calls. So there you go. I had a couple of thoughts when I was looking at that last slide. take time so try to relax, do prepare. Do not wait until the last minute to prepare your formula sheet if you're allowed to do so. Don't wait until the last minute to study a formula sheet that is provided to you. Give yourself plenty of time so you can study on both of those situations. So just writing stuff down cold on a sheet of paper is not going to help you. So try to stay relaxed, and best of luck.